Welcome. There's not as many people here, so I don't need the mic as loud. Try that again. Okay. Well, welcome. So this is our first review session. My plan is to at least get a good way into Chapter 4 in this one. We'll start with Chapter 1. We'll just see how things go. Typically, what I like to do is go for about an hour and a half. And then that's typically, students are getting worn out by then of an hour and a half being here. And then if you want to stay and ask questions about the practice final or anything else, then we can stay for another half hour. Okay? So my plan is, I have posted for my class, I've posted, or both my sections of 151, the study guide. It's in the practice exam folder in BB Learn if you don't have it. And it kind of just lists all the topics. So I figure a good way to do this would be to kind of just go down the list. Things you're pretty clear on, we'll just go through very quickly. Things that you want clarification on, let me know, and we can work extra problems. We can discuss it more or whatever. All right? Sound like a plan? Okay. So Chapter 1 is fairly basic. Kind of just some review things. Obviously, the first thing on the list here is the metric system. You will see the metric system throughout the final. You will see prefixes like kilo and nano and milli and things like that. So make sure you know what they are. Okay? So take a quick look at those. Most of the common ones are pretty easy to recognize. Skipping centi that's up there. Kilo is 10 to the positive third. Millis 10 to the negative third. Micro 10 to the negative sixth. Nano 10 to the negative ninth. And pico 10 to the negative 12th. Okay, so they're essentially every 10 to the third. Centi is kind of an outlier, but that's one that's still commonly used at 10 to the negative second. Okay? So know the metric system, you'll see that. The next one's kind of odd. I mean, obviously, there will be numbers in scientific notation. You're used to that. So I don't think that'll cause any issues. Sig figs. Okay. So certainly you need to be able to look at a number and know how many significant figures it has. Okay, that's one thing. But then also if you multiply, divide, add, subtract. Okay? And the only thing where you really have to, when there's any doubt is whether it's significant or not. Let me just get some space here. Are zeros. And there's three types of zeros. We have a zero something like that one. Okay. Zeros like that, or something like that. Okay. So the first one on the list is called a captive zero. Okay. Where it's between two non-zero digits. These ones here at the front of the non-zero digits, those are called leading zeros. And the one at the end is called a trailing zero. Okay? If it's non-zero, it's significant. So what about these trapped or captive zeros? Significant or not? Significant. Those are significant. Okay, so those are always significant. So this... Okay, what about leading zeros, as in the second number? Yeah, these are not significant. Okay, so they're just telling you where that decimal point is. Okay, so this number would just have 2, the 5 and the 6. This first number we didn't say, but that would have 3. And then what about this trailing zero? What's that? Is it? That's one that depends. It can be, but it may not be. What determines whether a trailing zero is significant? What's that? Decimal point. Okay? So this is not a good way to write this number because the 2 and the 5 certainly are significant, but we really don't know about that 0. Now, we could do a couple of things. We could put a decimal point there if we wanted 3 sig figs. Okay, so if I put the decimal point, then that 0 is significant, and we'd have 3 sig figs. The other option is to write it in scientific notation, to write it as, we could write 2.5 times 10 to the second if we wanted 2 sig figs. We could write it as 2.5 times, 2.50, sorry, times 10 to the second if we wanted 3 sig figs, and so on. Okay? So trailing zeros may or may not be significant. It depends if there's a decimal point in the number or not. Okay? So that's just counting. Is everybody good with rules for multiplying, dividing, addition, subtraction? What's the rule for multiplication and division? Okay, the lowest number. Okay, multiply and divide go together. Okay, so you just carry in your answer the fewest number of digits in any of the numbers you're multiplying or dividing. Okay, so multiplying and dividing is pretty easy. Okay, so the fewest number of digits in any of the numbers you're multiplying. Okay, so that's pretty straightforward. Addition and subtraction is a little bit trickier. And what do we do with that? Okay, so the fewest digits, so addition, subtraction. Carry fewest digits after the decimal point. Okay, so if we were looking at, I don't know why these bullets won't go away, there we go. If we were looking at something like okay. Since the 12.1 only has 1 digit after the decimal point, we're just going to carry 1 digit in our answer. Okay. So we would just carry to this digit here. We'd round that up, so we'd round that to 20.8. Okay. So watch for that. Multiplication and division is really straightforward. You just look at how many digits are in each number. Whichever is the least, that's what you carry. Addition and subtraction, it's based on the decimal point. All right, good with that? Another thing in Chapter 1 was density. So by definition, density is what? Mass per volume. This is probably on the equation sheet, but you should know this. So certainly, given in mass and volume, you should be able to calculate a density, or you might be given density and volume and asked to calculate mass, or you could, what's the other option? Density and mass and calculate volume, but essentially given 2 of the 3 things and solve for the third. Okay. So density is pretty easy equation, pretty straightforward, just plug in and solve. Okay? So that was in Chapter 1. One of the big things in Chapter 1, dimensional analysis. And where you're going to see that mostly on this exam is in stoichiometry, or in converting, say, moles to atoms, okay, using Avogadro's number. Okay. I don't think, if I can remember, I don't remember the whole final. I don't think there's just a dimensional analysis problem converting like, inches to picometers or something. I don't think there's anything like that, but you'll see this concept of unit conversions for stoichiometry and other problems. Okay? So I think what we'll do is we'll probably save that doing dimensional analysis for when we convert from moles to atoms or use stoichiometry rather than doing those here. Okay? So there's not much in chapter 1. It's metric system, it's sig figs, density, dimensional analysis. There were a lot of dimensional analysis problems there, but that's essentially going to be used later in the course or later in the final. That was quick. I don't think all the chapters will be that quick, but so chapter 2. This chapter started getting into, or actually it really started with the early experiments on atomic structure. Okay, and I think probably most of you here tonight are in my class. I really like those early experiments, and I make you know some things about that, but other faculty who teach Chem 151 do not. So they don't really spend much time on those early experiments. So there are no questions on the early experiments on the final, since it is a common final. Okay, but you guys remember those, right? You remember the cathode ray tube experiment, the oil drop experiment, Millikan's oil drop, Rutherford's alpha particle scattering experiment. Those are all really cool experiments. But what those allowed us to do was figure out atomic structure. Okay, so the types of questions you will get, obviously counting protons, neutrons, and electrons in a neutral atom or in a charged species. Okay, so make sure you can do that for both an atom, which is neutral, or an ion, which could be a positive or negative ion. Okay? So when we go from an atom to a negative ion, what's happened? What's happened to that atom? If we have a negative ion, the atom has gained electrons. Okay, so that means if you have a negative ion, you're going to have more electrons than protons. Okay, and remember the protons don't change. The protons are what identify the element. Okay, so if you had something like, let's say I'll pick your favorite element. I need to pick something that's going to form an ion. Let's do selenium. Okay, selenium's right below sulfur, so it's in the oxygen family. Okay, so selenium compared to say selenium 2 minus. Okay, so remember if we write selenium, the protons are defined. Okay, and I cannot see these darn periodic tables in this room. What's selenium? 34. So selenium has an atomic number of 34. Okay, so that's 34 protons for each of those. And then you'd have to know the mass number to figure out the number of neutrons. But what's the difference in the electrons between those? Okay, so the atom has the same number of electrons as protons. The 2 minus ion has 2 more electrons. So this would be 34 electrons. This would be 36. Okay, so when we go from an atom to an ion, it's a change in electrons. Okay, protons stay the same. Otherwise, if you change the protons, you've changed the atom. So that's a negative ion. The other direction, a positive ion, would have electrons removed, taken away. As an example of that, we could have something like aluminum and aluminum 3+. Aluminum has an atomic number of 13. So aluminum 3+ would have how many electrons? Only have 10. Okay? Okay, seems simple, doesn't it? Seems like a long time ago we did this, but it seems so simple. Yes? Well, neutrons, you would have to have the mass number, and that will depend that the next thing on the list, isotope. Isotopes are of an atom have the same protons, obviously, the same atom, but they have different neutrons. So you would have to be given, I could say something like, you have aluminum 26. Okay, and so then it would be mass number, subtract the atomic number from the mass number, get the protons. Or we could change this. Let's make it a little bit different. Let's say this is aluminum 27. Okay, so 27 minus 13, this would have 14 neutrons. Okay, yes?
So the number of neutrons can change?
It can change, yes. So that, most elements have isotopes, so it has various. They'll have the same chemical properties, because the chemical properties are based on the nucleus attracting the electrons. Okay, and since the neutrons are neutral, they don't affect that. But yes, there will be different nuclei with different numbers of neutrons. Okay, and as an example, let me just do the kind of common one. Those are 3 isotopes of carbon. Okay? Huh? Well, they have the same protons, because it's the same atom. So, these are all carbon, right? So, if you look at the atomic number for carbon is 6. Okay? So, it's the protons that identify the element. So, all the isotopes of carbon would have the same protons. They're going to have different numbers of neutrons. Yes?
So, say on the exam you give us C14 or 6, so that 6 is going to be fixed, correct?
If it's carbon, it is, yeah. Whatever element it is, it's fixed for that particular element.
And particularly speaking, the one that's below or subscripted to the left on the bottom, right?
This one here, the 6? Yeah. Well, you could be given something like, we could write it like this. We could say carbon 14. Okay? So just by saying the element name, I've identified the number of protons, right? You can look at a periodic table, you look at carbon, and you find an atomic number of 6. Okay? Because it doesn't matter what isotope of carbon you have, it's always going to have 6 protons. Doesn't matter. If it's carbon, it has 6 protons.
And so right there, that example, carbon 14, 14 minus 6 to get the number of neutrons.
Exactly. So looking at this designation here, the mass number of, so this 14 is the mass number. So 14 minus 6 would tell you 8 neutrons. Okay? So again, it's the protons that identify the element. So those are isotopes. Carbon is one where carbon-12 is the most abundant isotope. It's about 99% of a typical carbon sample. Carbon-13 is close to 1%, and carbon-14 is radioactive, and it's only 0.0001% or something of a sample. Okay? Okay. But those are isotopes. We actually did talk, we didn't use the names cations and anions, but everybody knows what those are.
Cats are positive.
Oh, cats are positive. Yes, okay. So cation, positive ion, anion, negative ion. Okay, let's see. All right. One more thing as we're talking about ions. Make sure you know the common ions that are formed by some of the main families in the periodic table. So the halogens, say when they react to form an ionic compound, what type of ion will the halogens form? So fluorine, chlorine, bromine, and iodine. -1. So remember, for the nonmetals, when they react to form an ionic compound, they will tend to gain electrons to reach the noble gas. So halogens gain 1, -1 ion, oxygen group, so oxygen, sulfur, selenium, tellurium, -2. And what about nitrogen, phosphorus, arsenic? When we get down here, we start getting the metals, but nitrogen, phosphorus, arsenic, -3. And then for the metals over here, group 1, the alkali metals, +1. The alkaline earth metals, +2. And then the other one, there are a few select other ones, but the main one is aluminum. Aluminum is always +3. Aluminum is always +3. Okay? So as an atom, they're neutral, but when they react, okay, the alkali metals will lose 1 electron. The alkaline earth metals will lose 2 electrons and be +2. Aluminum will lose 3 electrons and be +3. Okay? What's that? Well, boron's an interesting one because boron is a metalloid, a semi-metal, so it tends to be more like a non-metal, and it ends up, when it reacts, it tends to share electrons. It doesn't necessarily lose electrons. What's that? Well, you're not going to see boron as an ionic compound. It's just not. Okay? So yeah, the metalloids are interesting because they have properties that are intermediate between a metal and a non-metal, but they're actually closer to a non-metal than they are to a metal. Okay? All right, let's see what else we have in Chapter 2. I can't remember any questions on final asking you about names of families on the periodic table, but we know the noble gases, the halogens, alkali metals, alkaline earth metals. Certainly know that these are the transition metals in the middle, but I can't remember any about naming families. I guess it's, I can't think of a question this way, but obviously it's good to know that things in the same column, the same family, have similar properties, and that's why they're arranged that way. It's actually arranged by valence electrons, as we found out later in the course. So that's definitely good to know. And then the last couple of things in this chapter actually started getting into calculations for atoms, converting to moles, and also converting to the number of atoms. Question?
Sorry, I'm kind of just backtracking. So, is it the top number that gives you the protons, like with like the carbon-14, or is it the bottom number that gives you?
It's the bottom number.
Okay, that's right.
So the smaller number, which is the bottom number, is the atomic number, which is the protons.
Right.
Okay. It's also the electrons if it's neutral, but it's it really is the number of protons, and that's what identifies the atom. The top number is the mass number, which is protons and neutrons. Okay? All right, calculations. We haven't really done any yet, so this might be the time. All right, so calculating the molar mass of an element, we're really not going to do atomic mass. I mean, atomic mass is the same number, different unit, but we almost always use molar mass. Make sure, let's choose one that's not just an atom. Let's choose, let's do ozone. Let's do O3. Okay? So what would the molar mass of ozone be? If you have a periodic table with you. Well, so what is an oxygen? What's the molar mass of just an oxygen atom? It's about 16 grams, okay, per mole. We have 3 oxygens, so this is going to be about 48 grams per mole. Okay. So that's just for an element, but obviously you need to be able to do that for a compound as well. Let's just do a quick calculation. Let's say we have, I'll pick a number. Okay, we have 500 grams of ozone. How many moles is that? Okay. So you should be very familiar with this calculation. This is dimensional analysis. Okay, so you have to take the molar mass and arrange it properly so that we want to end up with moles. 1 mole of ozone, 48 grams of ozone. What does that come out to be? 10.4. And I wasn't good with sig figs, but 10.4 moles. So that's certainly one unit conversion that you need to be able to do for the final, one that you should be quite familiar with. The other one is going to atoms. So we could continue this calculation. So again, 500 grams of ozone. Oh, and let's actually go, let's see. Well, let's do molecules first. We could go atoms if we want. Let's do molecules. So sorry about that. It's a little bit messy. But how many molecules are in this sample of 500 grams of ozone? So the first thing we'd have to do with that, as we've already done, is we'd have to convert to moles, because we couldn't go straight from grams to molecules, so we'd have to go to moles first. We've already done that. So then what's the next step to go to molecules? Yes? Avogadro's number, exactly. Okay. So now that we have moles, we can take that 10.4 moles. Again, unit conversion, we want moles to cancel. We want to end up with molecules, and a mole of anything contains Avogadro's number of things, and so 6.022 times 10 to the 23rd. And so this comes out to 6.26 times 10 to the 24th molecules of ozone. Okay? So those were two important conversion factors in Chapter 2, where we really started using dimensional analysis, using molar mass to go from grams to moles, and then using Avogadro's number to go to moles to molecules or atoms or whatever that you had. Yes, Jesse?
So if we wanted to go to atoms, would we just multiply that number by 3?
Yeah, so if it did ask how many oxygen atoms do you have in that sample, each molecule of ozone has 3 oxygen atoms. So we could continue this if we wanted to. If we wanted the number of oxygen atoms, okay, we could take that. Take that number of molecules, and there are 3 oxygen. Well, let me not write 3, 0. Let's make it 3 atoms of oxygen per 1 molecule. Ozone. Okay? Again, another unit conversion. As all of these, you need to watch your units. So if we multiply what we had there by 3, I had the whole entire number still in my calculator, so I haven't rounded yet. So, well, maybe I did round at 10.4. On my ozone drop down below. Okay. Questions on any of those conversions? Grams to moles, moles to atoms, moles to molecules, whatever. Yes?
So if you're to give us like a compound, and you want us to find the number of atoms, would we just single out that particular element in that compound and see how many elements there are?
Well, it depends. I mean, I guess, depending on what compound you have, I mean, it could ask for a particular atom in that compound. It could ask for the total number of atoms in the compound, just depending. But yeah, I mean, you would do the same thing. I mean, if it asked for the number of oxygen atoms in glucose, for example, you would look at the subscript of oxygen in glucose, and then once you had molecules of glucose, you would just multiply by the number of oxygen atoms. Okay. Other questions? Yes?
This is not related to the exam in general. You said that it's common, and so does that mean that all of the chemistry professors are writing together?
Yes.
Will it still have a similar format to the exam?
The questions, so the questions should be pretty similar. I think the questions are pretty straightforward. What makes the exam difficult is that it covers most of 12 chapters worth of material. Okay, so there's a lot of material there. I don't think any of the questions are particularly tricky or hard. So I think it's pretty straightforward. The thing that's going to look different to you when you get the exam, if you're in my class, is for the final, we use a test generating program so that we can vary it each year. So the program we use changes numbers. For some questions, we'll have 6 questions written for a particular question, and so that it pulls one of the 6 so that it randomizes the exams each year. We add new questions each year, but we kind of have it randomized. So the way this program actually prints out the exam, the formatting's okay, but it will look formatting-wise, look a little different than my exam. But it'll, I think you'll recognize the questions. It's not like they'll look way different or anything. Okay? All right. Anything else? And we're up through chapter 2. You guys okay over there? Oh, are you close to done? Alex bringing out some hostility in the classroom. All right. What's that?
Okay, I got better at it. But at the beginning of the year, I would literally be like, I need to take a break. I'm getting angry. It was so frustrating.
Yeah. I think it particularly once we got to stoichiometry, it wasn't very nice when it came to stoichiometry. All right, let's not talk about Alex right now. Let's get back to final exam. Well, we'll get really distracted. Yes.
I'm sure you were in school, so I'm sorry. Avogadro's number, is that going to be on the equation sheet?
Yes, and I haven't posted it yet. I will do so tonight or tomorrow because I have to get a copy. Because I don't know if I have the exact copy that was put on the final, so I have to get it from the professor who does all the test generating stuff. But I will post it in Blackboard, so you'll see what the equation sheet looks like. There will be solubility rules there. There will be a periodic table, of course. So I will post that. Okay. So make sure you look in Blackboard in the practice exam folder. There is this study guide. There is a practice final. There's actually a couple, but they're very similar. One just has multiple choice format, but there's a lot of problems to work. And I'll post the equation sheet there as well. Yes?
Sorry, I don't even want to get off the track of Alex, but I noticed that you put in the grade for Alex on the 6th. When will that be updated?
Well, I'll probably update the objective score this weekend. And I'll probably, when I update the objective score this weekend, I'll update the pi score as well. Okay? But so if you finish the pi sometime this weekend, then it'll give you a pretty realistic grade. But the pi is not officially closed until Tuesday night for my class. So if you're in somebody else's class, for my class, it's not officially closed until Tuesday night. So for some, I will update the pi score again Wednesday morning of next week. But I will update it this weekend as well. And the objective score will be done because the objective closes tonight. Okay? All right. Just since we were talking about the exam, I don't know if I've mentioned this, but the exam is 50 questions. It is multiple choice. I would say the average time for most students to finish the exam is about an hour and a half. Some students will be done in an hour, maybe less. There is always about 10% of the class that is there to the bitter end. Just can't turn it in until I grab it from your hands. Okay?
Are you going to post a detailed key of the practice?
Oh, boy. Oh, I don't know. I don't have a detailed key of the practice final, so we'll see. It depends on how motivated I am this weekend. The semester's over for me. I'm not that motivated. We were photocopying final exams today, so it's like once I start photocopying final exams, I'm like, oh,
One of my teachers just straight up made the final optional.
oh, an optional final. I like that. Not for this class, though. I've done that for summer classes because they're so short, but not for a regular class. Yes?
Would it be like a detailed key or video?
It'd probably be video because the video key, I don't know if it's actually shorter, but in my mind it feels shorter because if I have to type up all the solutions, I get really bored after a while. So we'll see. I'll try. I'm not feeling really motivated right now. Okay. So I hate to tell you that since you guys have finals coming, but in my mind, my semester has kind of left me right now. Okay, yes. One more question, and we're going to get back to the material.
Did both of your classes hit the 75%?
Oh, I haven't looked. One class did. Section 7 did. Oh, hang on. I need to... Oh, both made it. Section 6 is at 76%. And Section 7 is winning. The rivalry between Section 7 and Section 6. Huh? Oh, 6% for the winner. Oh, that would be nice, wouldn't it? You're all winners. There you go, okay? What's that? Okay. So that means I will add 3% to everybody's final exam score. Okay, let's get back to doing some review stuff. So Chapter 3. Certainly know the first bullet there for Chapter 3. Certainly know how to recognize an ionic compound from a molecular compound. Okay, does everybody know how to do that? So ionic, what are we typically looking for? Metal cation, non-metal anion, or metal cation with polyatomic anion, like nitrate, sulfate, carbonate, phosphate, things like that. Okay? But typically, if you for our purposes, if you see a compound with a metal, it's probably a good chance it's ionic. Okay? So it's going to be a metal with a non-metal, metal with a polyatomic anion. Okay? What about molecular compounds?
Non-metal, non-metal.
Non-metals. Molecular compounds are composed of non-metals. Yes? No. Good question. Do you need to know any specific polyatomic ions? The solubility chart is there with polyatomic ions in it, and I think all the polyatomic ions on the exam are in the solubility chart. So make sure you realize that, because you might have to turn to the solubility chart to know what the ion is. But the solubility chart has carbonate and nitrate and phosphate and chlorate and hydroxide, kind of the common ones are in the solubility chart. Sulfate. Okay? Good question. All right. Next one. Do you know the difference between an empirical and a molecular formula? What is a molecular? Well, molecular formula. So molecular compound is composed of nonmetals, but what is a molecular formula?
It's the actual.
Very good. This is the actual formula of the compound. Okay, so the true formula, what it really is, what is the empirical formula? Simplest whole number formula. Okay, so as an example, let's not do that. If we had glucose, okay, that is the molecular formula of glucose. That's its actual formula, so that is the molecular formula. What would the empirical formula look like? Yeah, divide by 6 and we get CH2O. So this is the molecular. This is empirical. All right, let's see what else we have. Molecule diatomic, you don't need to know that. Write formulas of ionic compounds. You certainly need to know how to do that. So let's say let's choose. I'm trying to think of a somewhat difficult one. Let's do a couple. Let's do sodium with nitrogen. Okay, let's do that one. And let's do aluminum with oxygen. So we want to write the correct formula for those ionic compounds. So how are we going to do that?
First you check the periodic table.
Check the periodic table. So sodium is in group 1. It's an alkali metal. So what type of ion is sodium going to form? +1.
Nitrogen is 3 in on the other side, so it's going to be -3.
Okay, so nitrogen is going to form a 3- ion. So again, remember the nonmetals over here on the right will gain electrons to reach the noble gas. For nitrogen to reach neon, it's going to have to gain 1, 2, 3 electrons. Okay? So, what's our formula going to look like? Okay, Na3N. And we won't leave the charges in there. When we write the formula, we'll just write it Na3N. Okay? So your charges do have to balance. What's really happening is sodium is losing electrons. Nitrogen is gaining those electrons. Nitrogen is going to gain 3, so sodium has to give nitrogen 3 electrons. Well, each sodium can only give 1 electron, and so we need 3 sodiums. 3 sodiums, each giving 1 electron to give nitrogen 3. Okay? All right, what about aluminum and oxygen? Aluminum is always 3+. We'll always lose 3 electrons. What about oxygen? Oxygen will gain 2. Okay, 2 away from the noble gas neon. So what does this formula look like? Al2O3. So cross your numbers. Okay, and we would clean this up. Al2O3. Okay, so you certainly need to know that for the final exam. Yes? Yeah, molecule, diatomic molecule, like O2. I don't think there's anything that tests you on definitions that I can remember. Okay. All right, next one. Molar mass of a compound. Does that cause any issues?
You just end up doing it pretty. You just
Just-
have to add them up, right?
Just add them up. So again, I don't know why I have glucose on the brain. Maybe I need my blood sugar's low. Who knows? So glucose, just add up 6 carbons at 12.01 each, 12 hydrogens at 1.008, 6 oxygens at 16, and you should get, if you do that correctly, somewhere about 180.2 or so. Okay. If you carry more sig figs, it would be a little different, but just add them up. Good with that? All right, let's see what else we have in chapter 3. All right, we already did this above, so I'm not sure we really need to do this here. The book we're using is kind of odd in the sense I think of these as the same thing, but in chapter 2 it does grams to moles to atoms, for an element. And then in chapter 3 right after, it does grams to moles to molecules for compounds. There's no difference between those calculations. Grams to moles, you use molar mass. Moles to molecules, you use Avogadro's number. It's the same thing. Okay? So you're going to use the same conversion factors. If you want to go grams to moles, you would use the molar mass. Moles to molecules, you would use Avogadro's number N sub A. Okay? We're good with that. We don't need to do those conversions again. We just did them not too long ago. All right, next one. Know what the subscripts in a formula mean. See if I can come up with a different formula so we don't get away from glucose. Let's do something simpler. Let's do carbon tetrachloride. So we have a subscript of 1 for carbon. We have a subscript of 4 for chlorine. What do those mean? What does it mean?
The amount of the atoms that there are.
Okay. Okay, so we could read it as in one molecule. There are how many carbon atoms? 1 carbon atom. And how many chlorines? 4 chlorine atoms. Okay. But we can scale that up quite a bit. We could scale that up to a mole, which is what we do quite often. So we can also read this in 1 mole of that compound. How many moles of carbon do you have? 1 mole of carbon. And how many moles of chlorine? 4. Okay. So that will become important when we determine empirical formula, because we're going to read those subscripts as moles. How many moles of a substance in that compound, not necessarily as atoms. But we can read it both ways. We can say in 1 molecule, how many atoms do we have? We can say in 1 mole of that compound, how many moles of each element do we have? Okay? All right. Next thing on the list, mass percent. So since we have carbon tetrachloride already up there, let's say we want the percent carbon in carbon tetrachloride, mass percent. How would we do that? Yes?
Would we assume that there's 100 grams?
That's coming. That's for the empirical formula. But we do want to make an assumption here of amount of substance, but it's different than 100 grams. Yes?
Total mass of the compound, and then whatever you're looking for in this case carbon,
Okay, so what do you mean by the total mass? What mass are you calculating for that compound? Molar mass, okay? So in a sense, we are assuming we have 1 mole of that compound, okay? And so since we want mass percent of carbon, it's going to be the mass of carbon divided by the mass of the compound. And that would be a fraction, so part divided by the whole, right? Okay, but the key is, you might as well assume an easy amount of substance, that we have 1 mole of carbon tetrachloride, because then we can calculate the molar mass. Okay, so calculating the molar mass, we have 1 carbon at 12.01. We have 4 chlorines at 35.45. So our total mass of that compound is 153.81. In 1 mole of that compound, we have 1 mole of carbon, as we just discussed, subscript of 1. So 1 mole of compound, 1 mole of carbon. So 1 mole of carbon is just 12.01 grams. Okay. So again, mass percent, the mass of what you're interested in divided by the total mass. And assuming 1 mole of compound is the easy assumption here, multiply that by 100. And I get about 7 I guess we have at least 4 sig figs, 808%. Okay, so that's the percent carbon by mass. Okay, so most of the mass of that compound is due to chlorine. Okay, looks like over 92% of the mass. Okay, so that's mass percent. Pretty easy. It's just a fraction, part divided by the whole. The part you're interested in divided by the whole mass. Okay, now we're going to use that in the next step to determine an empirical formula. Okay, and that's where your suggestion of assuming 100 grams comes in.
Right.
Okay?
Wouldn't you convert that percentage into grams?
Yes. Yes. So do we want to do a sample calculation here for empirical formula? All right, let me see if I can come up with, let's see. Okay, let's do this. Let's do a simple one. So let's just do 2 elements. Percent carbon Okay, so you have a compound that's just composed of carbon and hydrogen. Those are the percentages. Calculate the empirical formula. Okay, so where do we start with that one? Yep, so if we, again, we could assume any mass of sample, but why we assume 100 grams here typically is because those percentages convert directly to grams. Okay, so 85.63% of 100 grams is going to give me 85.63 grams of carbon. 14.37% hydrogen of 100 grams is just going to be 14.37 grams of hydrogen. Okay, so we have mass. That's easy. What do we do with that mass? Okay, find the molar mass so that we can get what? We can get moles of each of those. So we just talked about you can read the subscripts as a mole ratio between those elements. Okay, in carbon tetrachloride, it was 1 mole of carbon for every 4 moles of chlorine in that compound. So reading the subscript as moles, if we can convert these to moles, 1 mole of carbon is 12.01 grams. 1 mole of hydrogen, 1.008 grams. Read that right off the periodic table. Gives us 7.130 moles. Okay. Those aren't super far away from whole numbers, but they're not quite whole numbers. Yes?
So would you ever ask a question where we're trying to find the percent of an actual molecule as opposed to the individual atom?
No, not for an empirical formula problem. I mean, yeah, I'm not quite sure exactly what you mean by a percent of a molecule.
A mixture?
Oh, a mixture. Oh. No. I'm just trying to think what that problem would look like, but we're not going to give that to you. That'd be interesting, though. Maybe you should put that on. Oh, I already photocopied them. Darn. Okay. All right. So this one does come out pretty close to whole numbers, but we should still do the next step because a lot of them will not be like this. So that would be a correct formula. That's the correct ratio between carbon and hydrogen, but we want whole numbers. So what do we typically do here? Divide by the smallest. And I believe this should come out, since I just did the calculation, it should come out to CH2. Okay. Questions on that? So that would be the empirical formula. Yes?
Molecular, they just give you like a large mass.
Well, yeah, so then we can continue this if we wanted the molecular formula. I'd have to give you the molar mass. And so let's say the molar mass is about 84 grams per mole, approximately. So what do we do there to go from empirical to molecular?
Divided by the molar mass of CH2.
Okay, so divided by the mass of CH2, so the empirical mass. Okay, so you're going to have to calculate this mass and compare it to the molar mass. Typically at this point you don't have to use exact molar masses. We could say 12 for carbon, 1 for each hydrogen. This mass is going to be approximately 14 grams for a mole of the empirical formula. So now we have 84 and 14. What's next? Yeah, divide the larger by the smaller. And if you've solved this correctly, you should get a whole number at this point. And for this one, assuming I did my calculation right, you should get 6. So what does that tell us?
That's what we multiply CH2 by.
We multiply CH2 by 6 to get to the molecular formula. So there's our empirical. Our molecular is 6 times that, which will give us C6H12. Questions? Okay. So this would be the true formula of the compound. This would be, this could be hexane or cyclohexane or some molecule like that. That's the actual formula of the compound. But obviously, if we want a simpler ratio, we could divide by 6 and get CH2. Okay? All right, last thing in chapter 3, balancing equations by inspection. Do we need to practice that? Let's do one? Okay, let me see if I can find one here. All right, let's do this one. Where do we start? What element should we start with? Start with carbon. Usually, not always, but usually it works out better to save hydrogen and oxygen for last. So we start with carbon. We have 2 carbons on the left. We only have 1 on the right. So let's add a 2 there. Then next step, once we have everything other than hydrogen and oxygen balanced, usually it's better to go to hydrogen next. We have 6 on the left, only 2 on the right. So what do we need? We need a 3. And then what about oxygen? Okay, so how many do we have on the right? 7. Okay, so we need to get 7 on this side. So what do we need to multiply by? 7/2. Okay, and so if you have one like this on the final exam, it will say balance with the smallest set of whole number coefficients. Okay, so this one we end up with a fractional coefficient. Don't let that freak you out. In this case, with this being 0.2, to get to 7, we have to multiply by a fraction. But that's not a big deal because we can then just multiply the whole equation by 2. And end up with 2 times C2H6, 7 oxygens, 4 carbon dioxide molecules, and 6 waters. And if you double check that just to make sure, it should still be balanced, of course. 4 carbons on each side, 12 hydrogens on each side, and 14 oxygens on each side. 8 plus 6 on the right. Okay? All right, that gets us through chapter 3. We've only been at it for a little over an hour. Let's keep going and at least get, I don't know if we'll get all of chapter 4 done, but at least let's get a good start on that. And if we don't get that done, we can pick up on Sunday. Did everybody get my email about the other times? So we're going to meet 1 to 3 on Sunday, same place. Come in through the main doors because I'm going to have to prop a door open. Okay, the building is locked on the weekend. So I will prop open one of the main doors. When you come in, try to make sure the rock stays in the door so that if other people come, they can get in. Okay, because otherwise you will not be able to get in the building. All right. So 1 to 3 on Sunday, and then the last one will be 6 to 8 on Monday, and our final is 10 a.m. Tuesday morning. Everybody knows what room we're in? We are, for the final, we are not in this room. Yeah. So section 6, so the 935 section is in the Wetaw Lecture Hall. So the building a couple down. And then section 7, we're in the Science Annex, room 106. If you haven't found those rooms yet or you haven't had a class in those rooms yet, make sure you find them ahead of time. All right. Really important part of this course, as you are aware, stoichiometry. Okay? So this was where we first introduced this concept. We came back to it a few times throughout the semester. But converting from amounts of reactants to products, or we can compare reactants, or we can go from product back to reactant if we want. I'm actually recording this, so in case you want to go back and revisit, but for students who are not able to be here. So when I record, my computer runs really slowly, so that's what that was. So what is the key? Actually, you don't. Let's cross this part out. We did not do that this semester. We didn't do excess reactant. Okay. So what's the key from getting from amount of one substance in the reaction to amount of another substance? Mole ratio. So okay. So if you have a problem where it gives you a reaction and it gives you the amount of some substance in that reaction, and it asks you about how much of another substance you produce, say, your first thought should be, well, it could be, might be a limiting reagent, but your first thought should be, I need to get to moles. If moles are not given, you need to get to moles. So whether it's, if grams are given, you need to get to moles. If molarity and volume is given, you need to get to moles. Okay? If it's an ideal gas problem and you have pressure, volume, temperature, yeah, that's a stoichiometry problem. You need to get to moles. Okay, so if you want to go from one thing to another, we're going to compare them in terms of moles. Okay, so always think, if it's a stoichiometry-like problem, and you should recognize stoichiometry just by saying, oh, you have so much of this substance in the reaction, how much of this do you need? Okay, moles. That should be your first step. Okay? All right, should we do a couple of stoichiometry problems? Yes? All right. Let me find a couple here. I've just flipped. This is a different book. This isn't a book we use because I thought I'd bring a different book just to pull problems from. And I flipped to the first stoichiometry problem I get to, and guess what the molecule is? It's glucose. Go figure. So we have to do that one. Okay. So we're going to react Okay, so there's a stoichiometry problem. You're given the amount of one substance in that reaction, and you're asked about something else in that reaction. All All right, so I think stoichiometry problems are pretty easy to recognize. We have glucose, we want CO2. So your first thought is? You need what? Moles of what? Well, you need moles of glucose. So we have grams. Your first thought should be, I need moles. Okay? So the first thing we need to do is get from grams of glucose. So always your first thought, get to moles. Because once you get to moles of glucose, you can now get to moles of anything else in that equation. You could get to moles of O2 if you wanted, or moles of CO2, moles of water. It doesn't matter, using the mole ratio. So in this case, we want to get to CO2. We don't want moles of CO2, we want grams, but we can deal with that. Okay? So always your first thought. If you're not given moles to start with, and it's a stoichiometry problem, get to moles. All right, so how do we go from grams to moles? Molar mass. Do we need to worry about oxygen? Does the problem say anything about oxygen? No. So if it doesn't say anything about the other reactant, assume it's in excess. Okay. This is certainly not a limiting reagent problem. We'll do a limiting reagent problem next, but this one, it just says the one reactant. Assume that's your limiting reagent, and that's what we have to worry about. So 856. Oh, that did not write. Molar mass. Add that up. Should be about 180.2, is that right? 180.16 or something like that. Close enough. Grams cancel. Again, check your units. That's dimensional analysis. Now we have moles, and then this is really the stoichiometry part. We go from moles to moles using the mole ratio. Mole ratio, coefficient for CO2 is a 6. Coefficient for glucose is a 1. And again, this is why you need to be proficient at dimensional analysis, because this is just setting up your units correctly to make sure you end up where you want. Okay, so I put moles of glucose in the denominator to cancel with that moles up in the numerator. Let's go ahead and just, since I ran out of room, let's go ahead and stop there. And then we can get to... Okay, so that gives me about 28.5 moles of CO2. Okay, the problem didn't ask for moles of CO2, it asked for the amount of CO2 in grams. Is that problematic? Now, what do we need? Molar mass. So carbon, 12.01, each oxygen about 16. You should get 44.01 for CO2 for its molar mass. Again, we want to get to grams. So we want grams in the numerator. We want moles to cancel. And it's 44.01 grams of CO2 in 1 mole of CO2. Moles cancel. And let's do the sig figs right. 856 only has 3 sig figs. So to 3 sig figs, this is 1.25 times 10 to the third grams of CO2. Is that right? Oh, it must be right. Questions? You guys should be familiar with stoichiometry. Okay. Any questions? All right. All right, let's talk about this next one. Probably, understanding the process by which a salt dissolves. You don't, that kind of skipped ahead, didn't it? You don't need to know per se, what's really happening when the salt dissolves is a dipole of water is interacting with the cations and anions of that salt and breaking the ionic bond and pulling that salt into solution. So that's what we mean by hydration. Probably more important for this exam is kind of knowing how a salt breaks apart when it dissolves. So say I gave you something like, let's see. Let's do this one. Okay, so we're going to take that salt, that ionic compound, and we're going to dissolve that in water. Okay, so that's a soluble compound. Most chlorides are soluble. We'll talk about solubility rules in just a second. But if you look at the solubility rules, most chlorides are soluble. So that salt is going to dissolve. Okay, but what do we mean by dissolving? What is that salt going to break apart into? What's that? Into ions. And so that's one thing you need to know, but you need to be able to predict what ions you're going to get. Okay, and the number of ions you're going to get. So that's where the charge comes into place. You're going to have to, as we kind of did earlier with writing ionic compounds based on charge, you're going to have to figure out the charges of these guys. Okay, so chloride is a halogen. So what charge will chloride have in that ionic compound? What will chloride be? -1. Gain 1 electron to end up at argon, electron configuration. You might remember aluminum is always going to have the same charge, but if you did not, you could go 3 times -1 is -3, so aluminum is +3. Okay? So when this salt dissociates into ions, breaks apart into ions, we're going to get an aluminum 3+ ion. And that AQ means that's the hydration process. That aluminum 3+ ion is surrounded by water molecules. And it was the interaction of the dipole with water with that ion that actually broke the attraction between aluminum and the chloride. Okay? So we get aluminum 3+. What else do we get? What do we get? Yeah. So be careful here. We actually get 3. Okay. So chloride is not Cl3. Chloride is Cl-. We just need 3 of those to balance that +3 charge of aluminum. Okay. So we actually get 3 chloride ions in solution. Okay. So once that salt dissolves, it doesn't exist as the salt anymore. It exists as these ions in solution, hydrated by water. Okay, so you have to know how that salt dissociates in solution. Yes?
So is anything with chlorine a salt? Or how does that work? How do you know what is a salt?
How do you know what the salt? Ionic compound. How do you recognize an ionic compound?
If there's a metal and a non-metal.
Metal and a nonmetal, or a metal and polyatomic anion. Okay, so right there we see aluminum metal with the nonmetal chlorine. That's an ionic compound. We also call those salts. Okay, and most salts are soluble, but we do have to look at solubility rules as well. Okay. Speaking of solubility rules, I think that's next. So let me give you a couple of examples. So let me just list a few salts, and then we'll look at, we'll say, is it soluble or is it insoluble? So let's do something like that. Hang on. I'm trying to remember all the solubility rules. Let's just do this one. Let's do one more. Okay, that should give us enough practice. Okay, so we're going to identify whether those, each of those is soluble or insoluble in water. Okay, so you will have the solubility rules. You don't have to memorize those. Of course, I don't think we don't have. Let's see. Let me just pop them out of the book here. So I don't think I brought a list with me. I guess I could Google a list, but okay. Most of that on the screen, most of it's there. All right. So let's do sodium sulfide first. And solubility. So the top part are the soluble ones. So let me bring this down just a little bit further. So sodium sulfide, soluble or insoluble? I think I hear mostly soluble. Okay, so we could just start at the top, and it says compounds containing alkali metal ions and the ammonium ion are soluble. So once you see sodium, you're done. Okay, you could, if you wanted to, you could come down to sulfides at the bottom, which are generally insoluble, but if it has an alkali metal or the ammonium ion, it is soluble. Okay, so you don't even have to come down to sulfides. You can just eat sodium ion and call it good. So that one's soluble. We'll put AQ after it because it will dissolve. Okay. What about barium sulfate? What is it? Insoluble. Okay, let's put an S for so it'll form a precipitate. So we'll put solid to indicate insoluble. So soluble for the first one, insoluble for the second. Most sulfates are soluble, but there are a few that are insoluble. So silver with sulfate, calcium with sulfate, strontium, barium, mercury, and lead. Okay. So again, most sulfates soluble, but there are some insoluble exceptions, and barium sulfate is one. So insoluble, what about silver chloride? That's also insoluble. So again, most chlorides, most halides are soluble, but there are three that are insoluble: silver chloride or silver halide, mercury, and lead. Okay? Good so far? Copper nitrate, copper 2 nitrate. Oh, we have to talk about naming. That's one thing I skipped. When I used to teach this course, I used to do naming more toward the end, so I pulled this list from last couple of years ago, so I think I have naming at the end. So copper 2 nitrate, soluble. Nitrates are soluble. So we see below the alkali metals, nitrates, bicarbonates, and chlorates are all soluble. And there are no exceptions. Okay, so that's soluble. Last one, iron 3 hydroxide. That is insoluble. Most hydroxides, it's way at the bottom here. Most hydroxides are insoluble. Okay, the only soluble hydroxides are alkali metal hydroxides and barium hydroxide. Okay, so that's just identifying the next step with those is writing reactions. Now, the good news for you in terms of writing reactions for precipitation reactions is this is a multiple choice test. It's kind of hard to have you write these, okay? So most likely what you're going to see is something like, what is the net ionic reaction, or something like that, okay? So let's look at one like that. So say you have, let me look at my solubility rules. All right. All right, so you mix those two soluble solutions together, and you could get a question like, what is the net ionic reaction? Yes?
So, since it is like multiple choice, don't you just look for the precipitate?
Mm-hmm.
So, and it only has like a precipitate, right?
So the net ionic could be no reaction. That's a possibility. You might not get any precipitate. Okay, but yes, the net ionic reaction is going to be the formation of the precipitate. So that's why I'm saying it's actually a lot easier on a multiple choice test than it is if I actually asked you to write out the molecular, the ionic, the net ionic.
And the precipitate is the one that's solid, correct?
The one that's insoluble, yes.
Okay.
Yes. So that's what I would do on these. It's probably helpful before you do that to assign the charges, although you'll see the charges in the problem. But, we could put a multiple choice where, this is actually iron 3+, and we could have one of the choices being iron 2+. So it's probably a good idea to assign the charges. We talked about chloride gaining 1 to be -1. 3 times -1, so iron is +3. We know sodium is +1. We also know sulfide right below oxygen, so sulfide is going to be -2. Okay? So now this is where you would want to take a look at your solubility rules and see, because our two possibilities are sodium combined with chloride. I think that one's pretty obvious, right? Okay? Our other possibility is iron combined with sulfide. Okay, so we know sodium chloride is not going to precipitate. What about iron sulfide? This would actually be iron 3 sulfide. What do we have? I'll switch back. What do we see about sulfides? Insoluble. So there's not many that are soluble. Iron is not on the list of soluble sulfides. So that's our precipitate. So now you just have to decide what the formula of your precipitate's going to look like. Yes?
Can you explain again how iron has a cluster charge?
Because chloride is one away, or chlorine is one away from the noble gas, and so chlorine's going to gain 1 electron and be -1. So 3 times -1 must mean that iron is +3 to balance that. Okay? Yeah, so make sure you can do that. I mean, assigning, writing formulas of ionic compounds from the charges or going the other direction is really important. You have to be able to look at something and figure out what the charge is. Because transition metals, we don't know exactly what the charge is for transition metals. They can have varying charges. So we have to use the other ion, the anion, to figure out what the transition metal is. Yeah. You do not carry the subscripts, no. You carry the charges. And we could write out this whole thing if you want, just to practice, but net ionic, we now know this is going to be our precipitate. So we're essentially going to write the reaction of that precipitate being formed. Okay, so we can shortcut to the correct answer, but we do have to write the correct formula of that. Hang on. We have to write the correct formula of that solid. And that would be what? Fe2. So cross your numbers here, Fe2S3. So we know that's our precipitate. So we know we must have 2 iron 3 plus ions combining to form that, and 3 sulfide ions. Okay? So without writing out and balancing the whole reaction, we know this is what we have to produce. And there's a subscript of 2, so we have to have 2 iron 3 plus ions. AQ, sorry. 3 sulfide ions. Okay, and again, these numbers I'm getting from the subscripts. Okay? So I must have 2 iron ions combining with 3 sulfide ions to produce that solid. Okay? So that's kind of the shortcut way to get to the net ionic without balancing the whole equation. Yes?
Is there ever a time where there won't be a precipitate?
It's possible.
Okay,
So you could mix those two solutions together, and if you looked and you went, okay, this cation with this anion, no precipitate. If we did the other cation with the other anion and there was no precipitate, then there'd be no reaction. Okay, it's possible, yeah. So if you want, you could write out the entire molecular equation, balance it, do the whole bit, but for net ionic, once you know what your precipitate is, the net ionic is the formation of that precipitate. Subscript 2, 2 iron ions, subscript 3, 3 sulfide ions forming that solid. Okay? All right, we are at about an hour and a half, a little over an hour and a half. Keep going. Yes? Yes. Oh, did we not do a limiting reagent problem? Oh, sure. I meant to do one. All right, let's do a limiting reagent problem. Let me just do it down here since I... All right. Sorry about that. I meant to do one. I just kept moving right along. All right, limiting reagent. Oh, that one's too easy. We don't want one that easy. That's too easy too. Okay, let's do this. All right, so let's balance this. So we need a 3 there, 4 there, 6, 10, 5. There we go. All right, so that's the combustion of propane. Let's react. Let's react 80 grams of propane with, let's see, I'm just trying to get good numbers here. Hang on. 80. Okay, so 80 grams of propane with 200 grams of O2. Let's ask again how much CO2 is produced. Okay. So if this problem were worded, we would, it'd be in a sentence. It would say, okay, 80 grams of propane is reacted with 200 grams of O2. What mass of CO2 is produced in grams? Okay. So first off, you need to recognize that as a limiting reagent problem, and you do that how? Yes.
Don't you find?
Well, don't tell me how to solve a limiting reagent. How do we know it's a limiting reagent problem? Well, that's stoichiometry. If it gives you amount of one thing and asks you for amount of other thing, yeah. Okay, yeah. So if you're given the amount of both reactants, okay, one of them's going to most likely run out first. Okay? Next question I have for you. Can I shortcut this problem and say this is a smaller mass, and therefore that must be my limiting reagent? No, because it's not by mass, it's by moles, right? And you can see we need 5 times more moles of O2 compared to propane. So, you can't just say, oh, this is less mass, it must be the limiting. You should probably do the calculation. So there's different ways to work limiting reagent problems. I like the method where you take each reactant separately and figure out how much product you could get. So if all of the 80 grams reacts of propane, how much CO2 could we get? Then let's do a separate calculation. If all the O2 reacted, how much CO2 would we get? So we're going to do 2 separate stoichiometry calculations. So let's do propane first. Might have to break down and get a new computer one of these days. All right. And let's stop at moles of CO2 because one of these calculations, the amount of CO2 will not be right. So you could go to grams in each one, but you might as well stop at moles because it'll save you one step in the calculation. All right, stoichiometry. What do we need? We have grams. What do we need? We need moles. 1 mole of propane. It's going to be about 44, right? Yes, about 44.094. So again, watch your units. Grams canceled. We now have moles, which is what we need. Okay, so again, stoichiometry. If you don't have moles at the start, get to moles. What's next? Ratio. So we want to get to CO2. We need that in the numerator, 3 moles of CO2 for every 1 mole of propane. Again, it's always good to just double check your units and make sure you write your units. Students don't like to write units down. I would take the time on the final exam and write your units down. Okay? Don't just write 3 and 1 with no unit there because you might flip it and write 1/3 and then you would be wrong on the calculation. So let's see what we get here. So this comes out to about 5.45. I'm going to carry a couple of extra sig figs to avoid rounding errors. So 5.4533. So what that says is that if all the 80 grams of propane were to react, that's how much product we would get. Now let's do the calculation for oxygen. If all the oxygen reacts, how much product could we get? Okay, again, first thought, if you don't have moles to start, get to moles. Okay, it is O2, so you have to take oxygen times 2, so 16 times 2. That gets us to moles of oxygen. And what's the mole ratio to CO2? 3 to what? 3 to 5. Moles O2 cancel. And this comes out to 3.7500. All right, so we have two answers. One is right, one is not. Which is the correct answer? The smaller one. So what happens here, O2 is our limiting reagent. This is limiting. It's going to run out first, and the reaction stops here. Okay? Once the O2 is gone, we can't make any more CO2 because there's nothing for the propane to react with. Okay? So propane is going to end up being our excess reactant. So this is the correct answer. The top one is not. So now that you know what the correct number of moles is, now you can convert to grams. Okay, so is there any question on these two calculations before we convert to grams? Everybody okay with? So essentially you're just doing two stoichiometry calculations in one problem. Okay, so that's not that big of a deal. Okay. All right, last step. We have moles, we want grams. Not too bad. Calculate the molar mass of CO2. It's about 44.01 grams per 1 mole. We get about 165 grams of CO2. Okay? Yes?
When you're doing it back to grams, the 3 in front of CO2 doesn't matter.
No, because this is, so that 3 in the equation is really just the mole ratio. So that factors in here. But we know the moles of CO2 that we have. And we're then just multiplying by the mass of 1 mole. So we don't have 1 mole of CO2. 1 mole of CO2 would weigh 44 grams. We actually have 3.75 moles. So the mass is obviously going to be larger than that. Okay. Yeah, but those coefficients, the only place you're going to use these in the calculation is here at the mole ratio. 3 moles of CO2 to 5 moles of O2, or 3 moles of CO2 to 1 mole of propane. Okay? All right. That's an hour and 45 minutes. Yes?
Can you go back up to the balancing equation?
The balancing equation or this balanced equation?
I know the one before.
The one before this one.
Or not the balancing equation, sorry, I meant the net ionic.
The net ionic. You just want to see it, or do you have a question about it?
To make sure I wrote it down.
Okay. All right. So I think that's enough for now. Now, if you want to stay and you have any questions about particular things, like whether it's on the practice final or just anything else that you're having trouble with, I'll stay for another 15 minutes. But again, we'll meet on Sunday and also on Monday, so we should have enough time to make it through all this material. Chapter 4, solution stuff, molarity, dilution, solution stoichiometry.
Are you going over that next time?
Yes. Yeah, so it's essentially molarity, dilution, solution stoichiometry is what's left in Chapter 4. Okay? We'll do that Sunday. Make sure you realize one thing I forgot to do that's in Chapter 2, I believe, or maybe 3, is naming. So we're going to have to come back to naming, because you do have to know how to name compounds. And some semesters I do it later in the semester, and when I pulled this old study guide, I didn't think about that. See you later.
So I understand how you got 14 grams. Is that
You just said that's just 12 for carbon, 1 for each hydrogen is 14.
And then how did you get 84?
That would be given.
Oh. Okay.
Yeah, so it would say in the problem the molar mass of the compound is
Oh,
this.
Okay, okay.
Okay?
Thank you.
Yep, no problem. Uh-huh.
So I know the volume is inversely
Inversely proportional, yeah.
Yeah, but then I put true on that one. How is that?
Well, but it says the gas is compressed. So what does it mean about the gas is compressed?
Being pushed to?
Yeah, so it's being pushed on. So that's the opposite of it, the gas expanding. So the gas is being compressed. So if we squeeze on that
The
gas,
pressure is going to increase.
the pressure is going to increase and the volume is going to decrease. So they are inverse, but if you're compressing a gas, you're squeezing on the gas.
Okay.
So pressure is going to go up
So easy.
and volume is going to go down. Yes.
What about the limiting reactant when it has like the axis is something?
The what?
That doesn't matter. Like in the limiting reactant like this problem, and it says the axis is.
Oh, how much excess? We did not do that this semester.
Okay.
I skipped it because we were a little bit behind at that point. So there is no excess on the final. Okay? Yeah. Yeah. Oh, I guess I can. Hang on just one second. I'm still recording.